Welcome to the physics class for January the 19th. As you may have noticed, I'm not in my home office right now. I'm at the school, but I can't be in my room because Martha went and stole my room. So I'm stealing Mrs. Whitbeck Zacharias' room, but that's okay. Shouldn't affect anything that we do here. Before we start into the talking about the homework, which was of course the lab report, let's go over some general announcements. Okay, so you have hopefully now looked on Aspire and have seen that I have put in your test scores. And you'll see that those of you that turned in some work in hopes of getting partial credit, for the most part, it was a good thing that you did, because for the most part, you earned a lot of points from that partial credit. It made a big difference in your final grade. Those few of you who didn't do that, you're really missing out. Boy, it can pull your grade up a whole letter grade and sometimes even more. So the grade that you see in Aspire is now your final grade. Now, some of you may notice that I made a mistake. Oh, let's see, somebody just joined here. Let me let them in. Okay. All right. So some of you may have noticed when you look on Aspire, you're going to say, oh, Mr. Hendricks, you made a mistake. Because what I did was I told you guys that when I transferred the quiz scores in, on the quiz retakes, I said that although Canvas tells you that you're going to get a 10, when I transferred over into Aspire, I'm going to transfer it as a 9. Well, I'm really sorry, guys, but I forgot to do that. I know you're going to be disappointed. Now, the thing I forgot was not to transfer the scores over. I did do that. But I transferred them over as 10s, not 9s. I gave you guys too many points. Oh, I feel terrible. I know you're going to be very disappointed that I gave you too many points. But it's too late now. I'm going to stick with that. But next time around, at the end of this term, when I transfer them in, if you turn them in, if you take them after the due date, I will transfer them over as a 9 rather than the 10. So Aurora likes my sarcasm there. But I am serious that it is my intent at the end of this term, I will transfer them as 9s, not 10s. Okay, now I only did it if you told me that you retook the quiz. Because remember, I do not have Canvas automatically linked with Aspire the way that some teachers do. So if you retook a quiz and you didn't tell me about it, I don't know about it. You got to send me an email. Let's see, what other announcements? Oh, the test rework. That, as usual, it is going to be a required assignment for you to go back and redo the quiz or redo the test. If you look on Aspire, you'll see it has appeared now as a new assignment in Aspire. It's the same questions as before, but it's a new and different assignment. And the point value on the questions have been adjusted. But you need to do that. And I'm going to put a deadline on it of this Saturday. I think that's not an unreasonable amount of time, especially given the fact that Friday is a work at home makeup day. You don't have classes on Friday, but Friday is still a school day, right? So I think it's not unreasonable for me to ask you to have that done by Saturday at midnight. And you do need to redo all of the problems, including the extra credit problem. So on the test, on the original real test, the last problem was an extra credit problem that you were not required to do. But on the rework, it now becomes a required problem. I want everybody to know how to do that. Like I said before, knowing how to use Desmos to solve super complicated problems might very well be the most important thing you learn in this class for some of you. So I really want everybody to do that. Okay, and then the only other announcement I can think of is to remind you that tutoring sessions are being held as normal, Tuesdays, Thursdays after school, Fridays, 11:30 to 12:30, and then Saturdays, the 2 different times during the day on Saturday. So you should already know about that. Please take advantage of that. Okay, any questions? All right, let's talk about the homework. Now, so I looked at the homework the lab reports. Now, I haven't looked at all of them. I just scanned them really quickly because a lot of you just turned it in like about 10 minutes ago. You really like cutting things close to the deadline there. But I did scan through them. And I think for the most part, it looks like you guys knew what you were doing. The equations that you came up with, interesting variety of the equations you came up with. So let's take a few minutes and let's talk about that. So what I'd like to do now is let's go into Desmos, or not Desmos, I will in a minute, but let's go into Canvas first. Okay, let me share my Canvas screen with you. Okay, so you'll notice module 6 now is the one that we're in right now. Pendulum Lab report was due today. Here are a couple of links that I put in Canvas that I think that you guys will find are helpful. These are not assignments that you have to do, but they are links to things that I strongly encourage you to go check them out. So one of these is the online pendulum simulator. And I know that some of you are going to say, hey, wait a minute, that looks familiar. Remember back on the first day of class where everybody did a different online experiment? Well, some of you did the pendulum lab. And so what I did was I just embedded that right here in Canvas. So let's go right straight to the lab. Let's skip the intro. And if you click on there, it'll take you to this nifty little online simulator, which you might, maybe some of you used this when you did the pendulum lab. I mean, I would hope that you used an actual weight and an actual string, but you might have been tempted to do this. So we can do the lab right here. So if I just pull this back a little bit, set it swinging. Okay, so we have a stopwatch here that we could use to time it. But we also have this really nifty thing, which just come up just a little bit. Here is a thing called a period timer, which actually I think is actually cheating. But if you did it, I'm not going to dock you points for it. I just think it's too easy if you use this. So let's see how it works. So if I click this, okay, so it starts and then it stops. So it only measures one cycle. You remember the way I told you guys to do it was measure 10 cycles because there's always a little bit of measurement error, right? It's a human reaction time, it's unavoidable. Well, with this software simulator, you don't have the human reaction time. So notice the period here, 1.6804. Now I'm gonna do it again. And hey, what do you know? I got the exact same number. Let's do it a third time. And surprise, surprise, it's the exact same number every time. So this is clearly not real. This is artificially generated data, but useful. So it certainly speeds things up. So what we could do then is we could come up to this control and we can vary the length of the pendulum. So there's 0.1, and so measure the time. Okay, 0.6361 seconds. All right, then let's take it up to 0.2. All right, there's 0.2, measure the period, and bingo, there you go. And then take it up to 0.3 and measure the period, and bingo. Okay, now notice we could also play with gravity, which is something you wouldn't be able to do in real life, at least not on the surface of the planet Earth. So this software simulator has a lot of neat things going for it. Now, how about the mass? Okay, so our period here is 1.1004. If I change the mass and then redo it, hey, what do you know? Changing the mass doesn't affect it, just like we talked about last time. Okay, so what I can do here is I can get all of this data from the simulator, and then I can put that into Desmos. And here I've already done it. So here is the data, and this is data that I got off the simulator, which is kind of artificial. And so now we need to figure out what equation to use. Now, when I scanned through your reports really quickly, I saw that many of you used a cubic function. So what you did was you added a new expression and you said y1 and then squiggle or tilde a times x1 cubed plus b times x1 squared plus c times x1 plus d. All right, and so this is the graph that you got. Wow, that looks like it fits pretty well. And remember R squared? I told you that R squared is the number that gives you an idea of how well your data fits. Okay, well, the R squared here is 0.9998. Wow, that is good. That is really, really good. And so many of you said, well, I think we got it. And there you went. Okay, others of you, instead of using a cubic function, others of you used a square root function. So let's do that. So here I add in a new expression. And so I do y1 tilde a times the square root. And I need to go in here to get the square root thing, okay, of x1. And I don't even need to do plus b because right there it fits really well, really well. And now if you look at the R squared value, you see the R squared is exactly 1, which should make you suspicious. Because hopefully you guys remember when I talked about this last time, I said that there's always going to be a little bit of measurement error. I mean, if you're doing an experiment for real, using a real pendulum, then it's unavoidable you're going to have a little bit of measurement error. And so in the real world, you're not going to get an R squared of exactly 1. So the fact that we got an R squared of exactly 1 would hopefully lead you to suspect that, yeah, maybe this data that we were using wasn't real world measured data. Maybe it was artificially generated data, which in this case is exactly what happened. The numbers came from the online simulator. So yeah, okay. So this R squared of 1 is definitely better than an R squared of 0.998, but not a whole lot. So which one of these is really the right one to go with, the cubic one or the square root function? Well, tell you what, let's zoom back out again and look at what happens if you go beyond the 1 meter range. You can see that if you go with the cubic, after you go past that 1 meter range, according to the cubic, which is the blue one, it says that the period should start going up. And that is not going to be what happens. If you were to do the experiment with 1.5 and 2 and 3, you'll find out that it actually does not go up. So the cubic function is not the correct function. The square root function is the correct one. Now, does that mean I'm going to dock you points if you said that a cubic was it? No, I won't. But I do want you to be aware that the correct function is in fact the square root function, not the cubic function, okay? All right, so I will look over your lab reports, probably not until the weekend. I've got a lot of stuff in between now and then. So over the weekend, I'll look over your lab reports and grade them and then get them back to you. Now, we're going to start today into chapter 14. And in fact, let me go ahead and share my screen with you. Okay. All right. So we are skipping chapter 12 and we're also skipping chapter 13, which I would do even if it wasn't a coronavirus year. Even in a normal year, I still skip those chapters just because there's not enough time in the year to do all the cool things. Your book is full of wonderful, great stuff that I hope that you will be interested in, but there's just not enough time to do it all. So we're going to skip to chapter 14. Now, when you read the chapter before you do the homework, because I know you always read the chapter before you do the homework, you're going to find that they're going to talk about pendulums. And they are going to tell you what is the actual equation for a pendulum. They're going to tell you that the equation that relates the length of the string and the period of the pendulum is this one that you see down at the bottom of the screen here. The period is 2 pi times the square root of L over G. Now, they don't derive that equation for you. They just tell you, trust us, this is the right equation. Now, that's against my religion. Okay, I firmly believe that No physicist should use an equation unless you have derived it yourself, unless you know where it comes from and you know that you can trust it. Now, some of you might say, but wait a minute, Mr. Hendricks, we did derive it when we did the lab. Well, that's not really a derivation. That's more of a confirmation. In fact, let's take a minute. Let's look at what they claim is the right equation. So I'm going to rewrite that. I'm going to put that as t equals 2 pi times the square root of L over the square root of G. And then I'm going to rewrite that to say the period equals 2 pi over the square root of G times the square root of L. Hopefully you guys realize I haven't broken any laws of mathematics when I do that. Okay, now will you guys please get out your calculators? And I want you to type into your calculators what is 2 times pi divided by the square root of G, where for G, let's call it 9.80. Okay, so please get out your calculators, type that in, and tell me what number does that work out to be. Calvin, go back and redo it. Will, okay, can you give me some more sig figs? Okay, Aurora gave me some more sig figs. Connor did it with 3 sig figs, which is the correct way to do it. And those of you that are doing 4 sig figs, your number agrees. Okay, so if we go with 3 sig figs, this number that I've circled there is 2.01. How does that compare with what we got up here? Well, look at that. According to Desmos, the equation of this graph here, if we use the square root function, is that the period, which is the y, equals 2.01 times the square root of the independent variable, which is L. So, hey, yeah, look at that. Okay, so our number and the number predicted from the book, they are in fact the same number. Now, some of you are going to say, well, then doesn't this prove that the book's equation is true? To which I say, no, it's not a proof. Now, it is reassuring confirmation. So that does lead me to believe that maybe the book's equation might be true, but it doesn't prove that it's true. So what I'm going to have you guys do, not today, but maybe next time we meet or maybe next week, we'll see how it goes. We are in fact going to derive this equation. We are going to prove that this is the right equation, but we're not going to do it today because we got other stuff that I want to do today. So for today, I'm going to violate my religious oaths. So please forgive me, okay? But I'm going to allow you to just take this equation and use this equation as if it was true, even though we haven't yet proven that it's true. And so in your homework tonight, they're going to give you some problems where they're going to say, okay, I got a pendulum that it's got a certain length. What is the period? Or they might say, here's a pendulum, and when we measure it on the surface of the planet Earth, we get this as our period. We take that exact same pendulum to some other planet where the pull of gravity is different. What will the period be on that other planet? So I'm trusting that you guys are not going to have any trouble with this. This is simple mathematics. Just 9th grade algebra is all you need. And you should be able to do all the pendulum problems in tonight's homework without any difficulty. Okay. So what else have we got in there besides just pendulum problems? Well, let's see. Okay. Springs. We are going to be working a lot with springs. And so a couple of things that you need to know about. So when I talk about a spring, or when the book talks about a spring, we're going to be talking about springs that look like this and not springs that look like this. So you might say, what's the difference? Well, very important difference. In this spring, you'll notice that in its natural state, when it's not compressed or extended, there are gaps in between each of the coils. Whereas with this spring, in its natural condition, the coils are touching each other. So that makes a huge difference. So with this spring right here, I could compress this spring, or I could extend the spring, and it'll work fine either in compression or tension. This one, I cannot compress this spring. If I try to compress this spring, well, because they're already touching each other, right? So that's like taking a solid metal bar and trying to squeeze a metal bar, and it's just not going to work. But it does work okay in tension, but it just doesn't work in compression. So all of the springs that we deal with in this class, well, let me say the overwhelming majority of them are going to be this kind. So it can be squeezed or it can be stretched. So make sure that when you hear the word spring, you think of this kind, not the other kind. Okay, and so what you're going to find is that if you take a spring and you don't put any force on it, so this is the length of the spring in its unstretched or uncompressed form. So if you take some weight here, and let's say we put a weight of a mass of m, and so the gravity pulls it down with a force of mg. So it stretches by a certain amount. Okay, now if we then double the mass, okay, so then that means that the amount of the force then is going to be doubled. So we've got 2 mg pulling down. Okay. What the book is claiming is that the stretch distance will double. So if we were to do an experiment where our independent variable here is the force that we are using to stretch or compress the spring, and then delta x is our independent variable. So this point right here is where x equals 0. And then these guys here, these are our delta x's. Okay, so the book is claiming that it's going to be a linear function. Now, is that really what would happen? Well, okay, let's look at our online simulator here. Let's go back to, oops, not that one. Let's go back to here. Okay, if you go back into Canvas, then, and you wait for Canvas to fully load. Okay, there we go. All right, so you'll see that I've put an online mass on a spring simulator on here, which comes from that same website that we used back on the first day of class, the PHET website, which they've got some wonderful simulations on there. So let's skip the intro and let's go directly to the lab. Okay, all right, so let's take a mass and let's put it on here. Now, one thing you'll notice is when I let it go, it oscillates. And we've got some damping here, so that shows this controls how quickly does it die down. Now, for what we're going to do here, I want no damping at all, which is not completely realistic, but it's going to make the math a whole lot easier. Okay, so once I set it in motion, it just keeps on going forever. And you can see here the breakdown of kinetic energy versus potential energy, which is not really what I want to focus on today. So let's get that out of the way here. Okay, and so what I want to know is I want to know how far does the string get stretched when I put the mass on there. So first off, I need to somehow mark where the spring is when it's not stretched at all. So here's my ruler, and so this is where the thing is when it's not stretched at all. Okay, and so now I put the spring on it, or I put the mouse on it and let it go. And then I say, okay, please stop wiggling. So there. Okay, so this is where, now I didn't pause the animation there. I just told it to stop wiggling. So this is where it will go when it comes to a rest. Okay. So you see here, it has stretched, oh, looks like about, let me zoom in a little bit here. Okay, so it looks like it's stretched about, what, 18 or so, whatever units that is. I don't know what those units are, if those are millimeters or whatever, presumably millimeters. Okay, so what if I change the mass? Well, you can see up here I can change it. So I can make it be whatever I want it to be. Did you see how the spring stretches there when I do that? And so then I say, okay, please stop oscillating. There, okay. So it has stretched. Okay, so in your homework tonight, they're going to give you a lot of problems like this where they're going to say, okay, so this is my x equals 0 position. And so this, from distance here, this is going to be my delta x there. And so if you were to do an experiment using this online simulator, and you play with the mass and take it all the way up to the maximum, okay? If you were to graph it, so we've got delta x is our dependent variable, and the force, which in this case is just going to be mg, okay? If you're to do this using the online simulator, you'll find that it's a linear function, and it's perfectly linear. And if you were to fit a line to it using Desmos, you'd find out that the r squared value equals exactly 1, which will hopefully make you a little bit suspicious and say maybe this isn't real data, maybe this is artificially generated data, which is true. So then what would happen if you did it with a real spring? Okay, now I'm not going to take the time to do it right now, but if I were to take a real spring and I were to stretch it, the data that you get would not be quite what you see from the simulator. Okay, what you would get, so here's our independent variable, here's our stretch. What you'll find is that it's linear for a while, but then it goes nonlinear. And at some point, the spring breaks completely. So we have this right here, which is the linear region. And then at this point right here, it goes nonlinear. Okay. And what's happening there when it goes on linear is that we are deforming the spring. So what's happening, we've got some deformation going on. Okay. And what you find is that if you take a spring and you stretch it past that point where it goes nonlinear, then when you let go of the spring, it will not spring back. So, I mean, if I just pull this thing a little bit and let go, it springs back to what it was before. Pull it a little bit more and let it go, it springs back. But if I pull it too much, if I exceed what's called the elastic limit, when I let go of that spring, it's not going to go back because I have permanently deformed that. All right, so that's the big difference between a real spring and the spring that you have in this online simulator. And so in all of your homework problems tonight, you can safely assume that we're using the spring within the linear portion of the curve there. And so as long as, go ahead. Go ahead. You had a question? Nope. Okay, so as long as you stay in that linear region, then you're within the region where the spring obeys something that's called Hooke's law. Okay, and the guy who came up with this, obviously his name was Hooke, he looked at things just slightly differently. Instead of having f be your independent variable and delta x being your dependent variable, he swapped those. Because you can do it that way if you want. What you can do is you can say, okay, I'm going to pick some distance that I want to stretch my spring, and that'll be my independent variable. And then what I'm going to do is I'm going to measure how much force does it take to stretch the spring that much. Okay, so a valid way to do it. And that's the way that Hooke chose to do it. So he says the force is proportional to the stretch distance, which is delta x. And sometimes you'll see they just write it as x because they assume that x initial equals 0. So if you make that assumption, then instead of calling it delta x, you can just call it x. Okay, there. Okay, so he said that the force is proportional to x, which is true as long as you stay in the linear portion. But once you go into the non-elastic region, then it's not proportional to x anymore, right? Okay, now I'm going to say something that you've heard me say before, and you're going to hear me say again. I don't like proportional signs. I like equal signs. What do I have to do? So if I change that proportional sign to an equal sign, what do I have to do? Anybody want to speak up and tell me? I can't just go replacing it. I can't replace that proportional sign with an equal sign. If I make the swap, I have to add in something that wasn't there before. What's that thing that I have to add?
Sigma?
A constant. Now you can call the constant whatever you want. Most of the time we don't call it sigma. Usually we use the letter K, but if you can use whatever you want. Okay, so what is the K value? Well, the K value is the slope of the line. So if F is your dependent variable and X is your independent variable, then the K value is just the slope of that line, right? And so what is it that might affect the slope of the line? Well, take a look at this spring here. Compare it with this spring here. What do you notice? Big difference, right? On this spring, the coils are made out of really thick metal, whereas on this one, they're really thin. So on this guy right here, I can compress him pretty easily. Okay, not too bad. And so I can stretch him equally easy. This guy right here, if I want to compress him, oh boy, is that ever tough. This guy is super stiff. This guy, not so much. And in fact, I even got another one right here. This is a longer one, but this guy, if I grab it and pull, this guy is really easy to pull. Okay, so this K value represents the stiffness of the spring. And in fact, it's got a name. We call it the spring constant. All right, so if I've got my three different springs here, and so I'm going to let my independent variable be the stretch distance. I like to call it delta X, but you'll see a lot of times the textbook just calls it X. Okay, and so then my force that I need to stretch it any certain distance, that's going to be my dependent variable. Okay, so if I've got this spring here that's really easy to stretch, okay, I find that it's going to be a relatively shallow slope. If I want to stretch it this much, I only need that much force. If I want to stretch it this much, I only need that much force, so not very much force. Now, on the other end of the spectrum, I take this really big, super stiff spring, and he's going to have a slope that's going to look like this, okay? If I want to stretch him just a little bit here, this stretch distance is what I want. So with the first spring, I only needed this much force, but with the second spring, I need way more force, okay? So the slope of my graph here for my stiff spring is going to be a whole lot higher than the slope for my not so stiff spring, all right? So in your homework tonight, they're going to give you some problems that I hope you agree will be really easy. They're going to say, okay, I got a spring, and so I use a certain amount of force to stretch the spring. Maybe I hang a weight on it, or maybe I just pull on it, whatever. I use some certain amount of force. Then if the spring constant is some number which they give you, then they're going to say how much is the spring going to be stretched. Or what they might do is they might tell you how far the spring gets stretched and ask you what is the K value. Or maybe they'll give you the K value and the stretch distance and ask you how much force is involved. So I mean, should be trivial. I'm hoping that you guys agree that that's going to be no problem whatsoever. Okay. Now, another thing that they're going to do in the homework is they're going to ask you how much work do you have to do to stretch the spring? This is going to be more interesting. Okay, so let me open. Oh, one other thing I just remembered before I move on. When you see Hooke's law written, okay, sometimes you're going to see it written like this with a minus sign in it. But other times you're going to see it without the minus sign. You're going to see it written as F equals KX. That's terrible. Let me try that again. I don't have my pen here. I'm using my finger to write with. And it's not as easy as when I use that pen. Okay, so sometimes you're going to see it with the minus sign, sometimes not. What's the deal there? Well, it depends on which force you're talking about. If you're talking about the force that you exert, so when you pull the spring, how much force is required, then you're going to want to use this up one. This is the force that you are exerting on the spring. But maybe what they're going to be interested in is how much force does the spring exert on you? And you guys know Newton's third law. For every force, there's an equal and opposite reaction force. So these two forces are the action-reaction pair from Newton's third law. So this is the one with the minus sign on it. That is the force that the spring is exerting on you. And this other one up here, this is this force that you exert on the spring. Now, most of the time, you're only going to be interested in the magnitude of the force, not the direction of the force. So most of the time, you can leave the negative sign out and have no problem. But in some of the problems where you are interested in the direction, then you are going to want to worry about the negative sign. So Aurora is asking a private question that only I can see. She says, will the circumference of the spring matter? And indirectly, the answer is yes. If I were to take this spring here and have an identical spring made out of the same wire, but it's going to be a smaller circle, that will affect the spring constant. But in the calculations that you're going to do tonight, don't worry about that. They don't really care about this size of the spring. All they're going to care about is the stiffness of the spring. And so they'll either tell you what the stiffness is, or else they'll give you the other information so you can calculate the stiffness. You'll never have to worry about that. Okay, so let's go back to the question about how much work is required to stretch a spring. Okay, so you guys know work equals force times distance. Now in your book, they like to say work equals force times distance d, but I prefer to call it delta x. So d and delta x mean the same thing. All right, so we know that if the force is constant, this equation works great, but with the spring, the force is not constant. So when I take this spring here, okay, let me take the easy spring here. This guy's easier. So when I first start pulling him, it's not too hard. But the more I stretch it, the harder it gets. And boy, now I get to this point, it's now really hard. So the amount of force that I have to exert changes as the thing gets longer. So I got a problem. How can I calculate the force if how can I calculate the work if the force is not constant? Somebody, you want to unmute yourself or type something in the chat box? What do you do when you want to calculate work, but the force is not constant? Come on. Somebody knows. Guys, we talked about this. Nobody? What am I going to do with you guys?
You find the area under, oh, you find the impulse, I guess.
Thank you. The area under the curve. Thank you, Jackson. You're now my favorite student.
Yeah.
But don't worry, the rest of you. The rest of you are my favorite student too. Okay. All right. Yeah, what we do is we take the integral, which is find the area under the curve. Okay. Remember this symbol right here? Okay. This symbol right here is called the integral. Now, some of you are saying, but wait a minute, Mr. Hendricks, that's a calculus thing, and I'm not in the calculus class. You don't need to be in the calculus class to know what it means. What it means is find the area under the curve. That's what it means. Okay, so if you've got a spring that obeys Hooke's law, as long as you stay within the elastic limit, you don't want to exceed the elastic limit. Okay, so the function looks like this: f equals kx. So if we want to find the area under the curve, well, that's not too hard to do. So if x equals 0, then f equals 0. And if x equals some arbitrary value, let's just call it some arbitrary x. Well, our y value here is really F, but F equals Kx. So this guy right here is K times X. All right, so we've got a triangle here. So the base of our triangle is X. The height of our triangle is Y, which is really F, which is really Kx. So that's Kx. All right, so the area then, let me make a little room here so that I can write. Okay, so area equals 1/2 base times height. So that's 1/2 times the base, which is X, times the height, which is K times X. So what does that work out to be? 1/2 Kx squared. So that is the amount of work that we did when we stretched the spring. That means that that is how much energy is stored in the spring. So in some of your homework tonight, they're going to tell you that you've got a spring that has a spring constant of such and such. You know, they'll tell you what the K value is. And they'll tell you, okay, we've stretched it by a distance of such and such. They'll give you a number for that. And then they'll ask you, all right, how much energy is now stored in this stretched or compressed spring? And you'll notice it doesn't matter if you stretch it by 1 centimeter or compress it by 1 centimeter, the energy is the same either way. Okay, and so all you have to know is just this equation right here. Oops, I erased it. Okay, when I stop sharing the screen, it goes away. But okay, so the work, which turns out to be the stored energy, is 1/2 Kx squared. And so now you know, and that's an X, not a Y. Okay, and now you know where this comes from. We have now derived this equation. So we can use this without violating any of my religious oaths. Okay. All right, so you're going to find that'll come in really handy tonight. Okay, but we're not yet done. There's yet some more stuff that is going to come in really handy tonight. Let's, oh, resonance, yes. Anybody know what bridge this is? Some of you took my engineering class. We talked about this in my engineering class. Anybody remember the name of this bridge? I know some of you took my engineering class. Come on. Oh, guys. Okay, this is the Tacoma Narrows Bridge. This is one of the most famous engineering disasters ever. Everybody who studies any kind of engineering, you will study this. This is an example of what you must not do. And this is so important here that I even put a link here. If you go into Canvas, you'll see that in addition to those 2 online simulators that I put there, I also have a link here for the Tacoma Narrows Bridge, for a video about the Tacoma Narrows Bridge. And when I did this, and then I tested it at home, it played for me just fine. But for some reason, when I try to play this now here at school, it's not working for me, but I think it will work for you at home. But even if it doesn't work at home, we can go directly into YouTube here. And let's see, let's type in Tacoma Narrows Bridge. Okay, so if you go to YouTube and you type in Tacoma Narrows Bridge, there's a whole bunch of videos on this one because it's such a famous event. This one here is my favorite one. So I'm going to play this video for you. And this is the original news footage. And it was done you can see back in 1940. And I just love the tone of the announcer. It makes me smile. So let me turn on my sound here. So I'm going to share this video with you. Now, I know that when I play videos over Zoom, it turns out to be pretty jerky, but I think that it'll still be valuable to do. So, can you guys hear the sound?
Yeah, we can. Yeah.
Okay, good. All right, here goes.
On of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saved himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes!
I love the narrator, and especially the music. I love the music; is great. So this is real. Yeah, I think it was a Silence movie back then, and then they just added the narration afterwards. But so anyway, this is real, and it's a classic case study that every engineering student has to study. And what happened is a phenomenon that you need to know about. Okay, it's called resonance. And so the best way to explain resonance is probably like this. So I'm going to take my spring here, and I'm going to take a mass, and I'm going to put the mass on the spring. Okay, so when I put it on it, it stretches the spring. But so there, okay, so the spring is stretched a little bit now. Okay, so what I'm going to do is I'm going to just give it a little tap. You see how it's going up and down there? Okay, it's got a frequency that it just naturally likes to vibrate at. Okay, if we were to do a bunch of experiments where we change the mass, so instead of using this heavy mass, I use a less heavy mass. Okay, and then we see how that affects the pendulum. What you'll find is that with this lighter mass, okay, it vibrates more quickly, and with the heavier mass, okay, it's more slowly, and it also the stiffness of the spring comes into play. If I use a spring with a small K value, a low spring constant, then the period tends to be a lot longer, or the frequency is shorter. By the way, frequency and period, those are two words that you need to know about. Maybe let's open up a whiteboard here. This is something that's really important. So you're going to hear me use these two terms a lot. Frequency is defined as the number of vibrations per second, whereas period is defined as the number of seconds per vibration. So hopefully you'll recognize that the two of them are just reciprocals of each other. So the frequency is 1 over the period. Or if you prefer, okay, you could say that the period is 1 over the frequency. Those are both completely either valid ways. Okay, so you're going to hear me talk about frequency and period a lot. And in your homework tonight, they will ask you to calculate the frequency. Now in tonight's homework, I'm not sure if they ask you to calculate the frequency. Maybe it's just the period, but certainly by the next time we meet, you're going to need to know both. Okay, so if I have a spring and I have a mass, okay, and I put it on there and I let it go, okay, it has a frequency that it just naturally likes to vibrate at. And what that number is for the frequency depends on what the mass is, and it also depends on what is the stiffness of the spring. So if I change the mass, it changes the natural frequency. If I change the stiffness of the spring, it changes the natural frequency. And so what happened with the Tacoma Narrows Bridge was that they had an extremely unfortunate situation where the wind caused some periodic disturbances to the bridge. And the frequency of the disturbances just happened to match the natural frequency that the bridge just naturally likes to vibrate at. I mean, so imagine this is a bridge, okay, and a car drives across it, sets up a little vibration, and it's going to continue for a while. Now, after a while, it'll damp out and stop, but for a while, it'll continue. And so that vibration is going to be a function of the mass of the bridge and the stiffness of the bridge. Okay, so if I hit this thing at just, let's say I hit it and I started vibrating. Then I come back again at some random time and I hit it again. And I come back a little later at some random time and I hit it again. The thing will keep vibrating, but it won't go crazy. However, it will go crazy if I time my hits so that the frequency of my hits just happens to match the natural frequency of the bridge. Okay, so let me hit it one time. Okay, so it's vibrating now at its natural frequency. So if I hit it and hit it and hit it and hit, you see what happened? It fell right off. Okay, so the frequency that I was hitting it with just happened by a funny coincidence to match the natural frequency of the bridge. And when that happens, then each oscillation gets bigger and bigger and bigger until the thing just finally breaks. All right, so there's a special term that we use for that, and it's a term that you need to know. And that term is resonance. Okay, so we say that resonance occurs if the period of the perturbing force happens to match the natural frequency that, and everything has a natural frequency. Every bridge has a natural frequency. Every building has a natural frequency. You know, the big tall skyscrapers that you see, if you go to New York City and look at these big tall skyscrapers, if a gust of wind comes along and pushes that skyscraper, okay, so imagine, okay, so here's the skyscraper. A gust of wind comes along, just one gust, and hits it. Okay, that skyscraper is going to it's going to oscillate back and forth a couple times before it finally comes to a stop. And people who work in the top floors of these big skyscrapers, they will tell you that sometimes they get seasick because they feel that motion. Okay, and so the period of that motion or the frequency of that motion depends on the mass of the building, depends on the stiffness of the building. Okay, so anytime that an engineer designs a building or a bridge or whatnot, they need to first do an environmental study and look at what are the frequencies of the winds. You know, you get certain turbulent patterns, certain eddies that form, and these eddies can give you periodic pulses. And so they need to do environmental studies and find out what is the frequency of those pulses, because as we learned from the Tacoma Narrows Bridge, if the frequency of the pulses happens to match the natural frequency of whatever structure you're building, then disaster happens. And you will be the subject of an old-timey newsreel as you watch your building collapse, and that would be very embarrassing, and people might die. Okay, so in your homework tonight, they're going to ask you questions about resonance. And I think that you now know enough that you'll be able to handle those okay. I haven't given you guys much of a chance to ask questions. Anybody have a question about anything that we've covered so far in class? Not hearing anything, not seeing anything. Okay, so you're ready to do the homework then, except you probably want to know what the homework is. Now, you know, of course, you can always look on Canvas and you'll see it on Canvas, but here it is. So make sure that you read the book before you do the problems, guys. Please do that, at least the first part of the chapter, and then do problems 1 through 13. And that'll be due next time. So there's no quiz today. You know, I thought about writing up a quiz for the Pendulum Lab, but yeah, I let you off the hook. Okay, so all you have to do is just the homework assignment, no quiz for today. All right, last chance for questions. Going once, going twice. Sold. Okay, so you can go ahead and type bye into the chat box. Remember, class is not over. We still have 20 minutes left. Use that time to read the book and work on the assignments. So you can go ahead and type bye in the chat box if you want. Now, if you did have a question, but you didn't want to ask it because you knew it was being recorded, here I will stop the recording. So take that away.